Hello students, so let us continue. So variation of conductivity, variation of conductivity with dilution, with dilution. This is the topic. Variation of conductivity with dilution. So now that's a point you can imagine. On dilution, conductivity decreases. Conductivity, or another term we use, specific conductance. On increasing the dilution, the conductivity decreases. Why it's so? That we already discussed. Because now we define conductivity for a unit volume. No, in the talk about 1 centimeter length between the electrons and 1 centimeter square area of cross section. So it's actually defined. The conductivity is defined in a very small volume. Okay. So what will happen if you dilute it now? If you dilute means now volume will increase. The total volume of the total volume of the electrolyte that occupied will increase, which means now the number of ions per unit volume decreases. The number of ions per unit volume decreases on dilution. That's the key point. If the number of ions per unit volume is larger, then conductivity will increase. Right. So we actually define conductivity for a unit volume of a small area. You can imagine that in the unit volume we define conductivity. So that's the point. The number of ions, number of ions per unit volume, number of ions per unit volume decreases on dilution. On dilution, the number of ions per unit volume decreases, hence no conductivity, or we will use specific conductance, decreases on dilution. On dilution means now you adding more water. On adding more water means now the ions have more space to occupy. So the number of ions per unit volume decreases, which means now the conductivity, use the term very correctly, conductivity decreases. Okay. So that's a term related to the conductivity. Now let us discuss variation of conductivity with dilution for a variation of molar conductivity, variation of molar conductivity, variation of molar conductivity, variation of molar conductivity with dilution. Now you imagine how the conductivity, molar conductivity, the term very important, molar conductivity varies on dilution. So now first point you have to come to your mind now, molar conductivity related to the conductance of 1 mole of an electrolyte. So all that the concentration available for an electrolyte is 1 mole. Okay, the concentration of 1 mole never going to increase. You adding 1 mole of an electrolyte to a particular water, then you add more water. So the number of the ions present in that available in an electrolyte is always the same, because 1 mole of substance you are taken. Okay, 1 mole of substance is there, and if you increase the dilution or decrease the dilution, doesn't matter. What's the matter in there? What's the electrolyte? How much concentration electrolyte is there? 1 mole. That never going to increase or decrease. Okay, so the point is, what will happen on dilution? Molar conductivity always increases with the dilution. Molar conductivity increases with dilution. Okay, now just imagine why it may be, because all that we have 1 mole of an electrolyte. On dilution what will happen? First point now, we can separately study for a strong electrolyte and weak electrolyte. First imagine for a strong electrolyte. For a strong electrolyte, what will happen? Both for strong electrolyte and weak electrolyte, the molar conductivity increases with the dilution, something that you can remember. For a strong and weak electrolyte, molar conductivity increases on dilution. That's the first point you can remember. For a strong electrolyte, you have to imagine, the molar conductivity will be, regularly it will increase. That's because, the ions are already, the ions present in electrolyte is already ionized. It's not that, it's have a low degree of ionization. It's already ionized. Strong electrolytes are already ionized at a moderate concentration. So the point that you have to remember, when you diluting it, there are two factors coming. One is yes, you can imagine more ions are separated. Okay, more ions are separated because dielectric constant of water is higher, so more ions are separated. So they contributing to the molar conductivity independently, both by cation and anion. Both ions, cation and anions, can independently contribute to the molar conductivity. That's the case because the force of attraction between the cation and anion is reduced due to the presence of this water as a solvent that we use. So the point is, for a strong electrolyte, you will see molar conductivity increases, that you can add on increasing on increasing the dilution. On dilution, more ions are get separated from each other, and the force of attraction between the cation and anion is also decreases. The force of attraction decreases means now the each ion, the cation and anion, can independently contribute to the molar conductivity. So that's a special case you have to remember related to the molar conductivity of a strong electrolyte. So you can observe molar conductivity. I can represent like lambda m. Molar conductivity increases steadily. Increases steadily on dilution. On dilution. This is something that you observe. For a weak electrolyte is definitely molar conductivity will increase, but this is due to the different reason. Here we already know weak electrolytes are partially ionized. So on dilution, it's what is helping. On dilution, more ions are now ionized. It's getting more ionized because it's a weak electrolyte. On dilution, it's helping to be more ionized. So degree of ionization will increase on dilution, which means now more ions are available. Hence force of attraction also going to decrease between the cation and anion when on dilution, which means we can say for a weak electrolyte the molar conductivity actually increases in a steep manner. It's certainly it will increase. Molar conductivity increases steeply on dilution. Why it's so? Now let us think why for strong electrolyte. Strong electrolyte because more ions are contributing to the molar conductivity, because now you will see on dilution more ions are separated from each other, and now the force of attraction between cation and anion decreases. Once the force of attraction is decreased, that really helps to these ions to contribute towards the molar conductivity. It's all about presence of ions. The ions are required. The ions has to be independent as we free from force of attraction. If that is possible, then they can definitely contribute to the molar conductivity. The conductance will always increase. So that's the point you can imagine due to from the strong electrolyte. First point, they are already ionized, so it's all about separating them, separating from each other. For on dilution, you will see, these ions are more separated from each other. Next point, they are the force of attraction between the ions, cations and anions always decreases on dilution. That increases the molar conductivity. Now I will plot the graph for you for a better understanding. For a weak and strong electrolyte, we can draw that. Now this is the case with the weak electrolyte. For a weak electrolyte, the chemistry is different because now weak electrolytes are poorly ionized. So degree of ionization increases on dilution. Degree of ionization increases on dilution. That's the first point that you can remember. On dilution, degree of ionization increases. So that definitely contribute to the molar conductivity, and now definitely as you more dilute, the force of attraction between the force of attraction between the cations and anions, between the cations and anions decreases. So that's the reason why on increasing the dilution or more you dilute, molar conductivity definitely increase for a strong and weak electrolyte. For a strong electrolyte you will see a steady increase, while now for a weak electrolyte you will see a steep increase. So let us draw the graph to get that picture. I am plotting a graph between a lambda m molar conductivity versus root C, where C stands for concentration. Concentration. First point you have to remember now, increase in concentration means no less dilute. Decrease in concentration means more dilute. Okay. This is the x-axis, this is the y-axis. Decrease in concentration. Decrease in concentration means more dilute. More water will be more, so concentration of the electrolyte will be less, on dilution. So concentration less means more diluted. So now imagine in this direction from left to right, now this is x-axis, the concentration increases, which means the reverse direction. Reverse direction, dilution increases. In this direction concentration increases means this direction dilution increases, or this direction dilution decreases, this direction dilution increases. Something you have to remember. Now how can you plot the graph for a strong electrolyte? It is observed that now as you increase the dilution in this direction, okay, on increasing the dilution, the molar conductivity actually increases for a strong electrolyte. This is the case for a strong electrolyte. You will see a steady graph increases. Now on dilution, molar conductivity increases. This is in this direction, molar conductivity increases. In this direction, the molar conductivity. In this direction, dilution increases. So increasing the dilution, molar conductivity increases for a strong electrolyte. Okay, it will be a linear graph, a straight line with a negative slope. That's what you generally obtain for a strong electrolyte. Let us discuss about weak electrolyte. Definitely on dilution, molar conductivity increases. It increases and then increases steadily. Now it goes as more the ions are more, it is ionized, the conductivity will be higher. Once now more ions are furnished means now conductivity increases rapidly. There is a rapid increase in the molar conductivity for a weak electrolytes. This is the case that different types of molar conductivity graph you obtain for a strong and weak electrolyte. For a strong electrolyte, there is a steady increase in molar conductivity. For a weak electrolyte, you will see molar conductivity increases first, then a rapid increase. More the ions are obtained, conductivity will be higher. That's simply because of the partial ionization nature of weak electrolytes. Okay, now let us think now. This is now a graph from which now you imagine a zero concentration. You diluting it, diluting it, diluting it, so much diluted so that now you can say the concentration of the electrolyte is almost nil at zero concentration, or we will say infinite dilution. You diluted that much, we can say that's a case where we can say it is an infinite dilution. At infinite dilution, the molar conductivity of an electrolyte now you can find, because now it's all about the what is the value of molar conductivity in the y-axis. In that point now concentration is zero, or that's point the molar conductivity at infinite dilution. So for a strong electrolyte you can easily extrapolate it to the y-axis. You just extrapolate it to the y-axis. That's the point you will get the molar conductivity at infinite dilution. You can represent lambda m0, where lambda m0 represent molar conductivity at infinite dilution. Molar conductivity at infinite dilution. So molar conductivity at infinite dilution for a strong electrolyte can be determined by extrapolating the graph towards the y-axis. Okay, the point now it meets the y-axis. That will be the point where now the concentration is nil. We can imagine concentration is zero, or that's the point we will discuss. That's the point we will say the molar conductivity at infinite dilution. So molar conductivity at infinite dilution can be found for a strong electrolyte. But it's not that much easy, or it's almost not possible for a weak electrolyte. Why? Because now there is a steep increase you will see for a weak electrolyte. So it's going up, it's going up, going up, going up. Not meeting with the y-axis. It's not meeting with the y-axis. So using a graph or normal method, you cannot able to distinguish the molar conductivity of a weak electrolyte at infinite dilution, because it keeps on increasing. For weak strong electrolyte it was a steady increase, so a linear graph we obtained with a negative slope. So that was possible for a strong electrolyte. For a weak electrolyte the difficult part now it's going up. So it's not meeting with the y-axis, which means now it's difficult to obtain the molar conductivity of a weak electrolyte at infinite dilution. So that's a point you have to remember. From the graph tells you the complete story. So practice yourself and now you can do it. Now what's the next point you can remember? Now, for a strong electrolyte, now it is more easy. For a strong electrolyte, we can have an equation: molar conductivity at infinite dilution. 0 represent at infinite dilution. Okay, molar conductivity at infinite dilution. Now we have an equation we have an equation for molar conductivity. Molar conductivity equal to molar conductivity of a strong electrolyte is equal to molar conductivity at infinite dilution. Sometimes you will see this word like this, lambda m0. This is also we have seen lambda m0 minus a root c. So this is the equation that you can remember to find the molar conductivity of a strong electrolyte. Where now this is actually an equation very similar to a straight line. We know for a straight line the equation is y equal to mx plus c. Then you will see it's an equation for a straight line where now we have a negative slope. If you take the slope, you will get minus A. And if you plot a graph between lambda m and lambda m and root c, you will get a straight line with a negative slope of minus A. And if you extrapolate at y-intercept, we will say that is C. Y-intercept is equal to C equal to lambda m0 or molar conductivity at infinite dilution. So that's the point, that's the equation you can remember for a strong electrolyte. Lambda m is equal to lambda m0 minus A root C. What is this A? A is nothing but A is a constant. A is constant depending on the charge of ions in an electrolyte. So it's all about that. It depends on the positive charge and negative charge. For example, in a Cl type, plus 1 charge, minus 1 charge. So A value for a electrolyte having a formula like this, AB. Now A plus, I can say B minus, having a similar A value. For a AB2, it will be similar. For a A to B, it will be similar, like that. A to B3, it will be different. So it's depending on the nature of electrolyte and the charge of the ion. No, A value varies. So A, you can remember, it's a constant depend on the charge of an electrolyte, charge of the ions in electrolyte, also nature of the electrolyte. So A value generally they gives. So A value is constant for a strong electrolytes. Okay, so now let us discuss the degree of ionization. Now we can express degree of ionization using our new term. We define degree of ionization previously. That time now we said degree of ionization or degree of dissociation. Degree of dissociation. Degree of dissociation represented as alpha. That time we define the number of ions produced divided by total number of molecules, or the number of molecules dissociated divided by total number of molecules. That's the way we defined before. Now we have the exact value. We have lambda m, molar conductivity, divided by molar conductivity at infinite dilution will give you the degree of ionization, because more the molar conductivity, degree of dissociation is always proportional, because it's all about first the ions has to be separated from each other. So degree of ionization is always proportional to the molar conductivity, and we will know the maximum ionization, maximum dissociation will take place at the infinite dilution. So take the ratio between the lambda m and lambda 0m, ratio between lambda m and lambda 0m give you the degree of dissociation. Okay, alpha value you can easily obtain. If you have lambda m value, you have lambda 0m value, so you will get degree of dissociation, especially for a weak electrolyte. For a weak electrolyte it's very difficult. For a weak electrolyte, they are partially ionized. But at an infinite dilution, where weak electrolytes are completely ionized. Something that you have to remember. Weak electrolytes are completely ionized at infinite dilution. If you dilute, that's the case. The case we will say molar conductivity at infinite dilution, and if you have the molar conductivity value, divide it. That will give the idea about the degree of dissociation, especially for a weak electrolyte. For a strong electrolyte, this almost will be similar, because both are having similar kind of a value, because even at moderate concentration, lambda m value will be closely related to the lambda 0 m as well. But no, not always the same, it will vary. But for a weak electrolyte, we can use this ratio between lambda m by lambda 0 m will give you degree of dissociation of a weak electrolyte. Talk about equivalent conductivity. We discussed what is equivalent conductivity yesterday. So equivalent conductivity again now similar. This time instead of 1 mole of an electrolyte in a 1 mole of an electrolyte in a molar conductivity, in equivalent conductivity it is all about 1 equivalent of an electrolyte. So just like molar conductivity, the equivalent conductivity also equivalent conductivity also increases for a strong and weak electrolytes. For a strong and weak electrolytes. Okay, independent whether it's a strong electrolyte, weak electrolyte, the molar conductivity always, sorry, equivalent conductivity is all variation of equivalent conductivity. Okay, more equivalent conductivity is also increases on dilution. The equivalent conductivity increases on dilution. On dilution for a strong and weak electrolyte. It doesn't matter, no, it's a strong electrolyte or weak electrolyte, the equivalent conductivity also increases. The chemistry is very much similar with respect to the molar conductivity as well. If you know the molar conductivity, that's a similar way equivalent conductivity also varies. For a strong electrolyte, it will be a steady increase in the equivalent conductivity as you plotted the graph as well, right? For a weak electrolyte, there will be increases steadily first, then there is a steep increase, rapid increase in the case of equivalent conductivity as well for a weak electrolyte. Okay, so let us wind up today and discuss more in the next class. Okay, thank you.